While watching this class, you will regularly need to pause the video to complete exercises. There are two platforms where you can complete those exercises. One, on the Accelerated Computing Hub. Two, on the DLI platform. For more information, please check out the intro section of the first video. All links can be found in the description below. Hi again, everyone. So in the previous section, we covered essential concepts like execution and memory spaces, vocabulary, data types, and parallel algorithm. We also created a functional 2D heat equation simulator. And although it currently runs on the GPU, our simulation still isn't making full use of the system's capability. And so in this section, we'll explore a few additional techniques to optimize the performance. So first, in section 2.2, we'll talk about asynchrony and how we can overlap communication and input-output to achieve 2x speedup. Then we'll learn the notion of CUDA stream and see how we can overlap computation with memory transfer. And finally, we'll learn and talk about pin memory and how to make the memory transfer synchronous and faster. So if we recap what's the current state. So the current state of our heat equation simulator is first, we copy the data from the GPU to the host and then write it to disk. Then, once this is done, we use thrust tabulate to compute the next set of temperature on the GPU. And we can see here that the CPU is launching the computation, and then the GPU is doing some the simulation on the GPU, the computation on the GPU, and the CPU here is waiting for doing nothing. So under the hood, thrust launches work on the GPU when we call thrust tabulate and waits for it to finish. That's because thrust tabulate doesn't return control until the transformation is complete. So while the transformation is happening on the GPU side, the CPU stays idle, it does nothing. And so this is a missed opportunity. And so if we want to write an efficient heterogeneous program, it means we need to fully use all the resources, which also includes the CPU. So can we find meaningful things for the CPU to do while the GPU is computing something? Well, yes, obviously. So first, let's look at the data dependencies. So the write step reads from the host memory of the previous operation, and while the compute step reads from the device memory. So because these operations use separate data, they don't depend on each other. As a result, the CPU can write the results to disk while the GPU is computing the next temperature. And so to achieve this overlap, we ideally split the thrust call into separate launching and waiting steps. Unfortunately, thrust doesn't support that, but thrust is implemented in terms of another core library, which is called CUB, and CUB supports the asynchrony we need here. So CUBs offers many sorting algorithms and just at a slightly lower level than what Trust does. And so we'll see how we can use all those algorithm iterators and types just like we did with Thrust. So first, let's understand better the difference between synchrony, like a synchronous operation and an asynchronous operation. So CUB is asynchronous. So it means that when you launch an operation from the host to be done on the device, so on the GPU, it immediately hands the control back to the CPU. So here, it launches the operation on the GPU and then directly gives you back control. That's not what Trust is doing. Trust is first launching the computation on the GPU by using CUB under the hood, and then it synchronizes using CUDA device synchronize to wait for the GPU to be done before giving you back the control of the CPU. That's why this thrust tabulate operation is blocking, because under the hood it's first calling CUB, which is asynchronous, but then synchronizing the CPU with the GPU, which means the CPU waits for the GPU to be done before continuing. So here we have an example with thrust where we compute the begin and end time to call thrust tabulate. We compute the begin and end time on the CPU. And so we can see that depending on the number of elements, obviously, the more elements we had, the more time it takes for the CPU, because the CPU here needs to wait for the GPU to be done. So the CPU is waiting for all of this time. So the more elements we have, the more seconds the CPU is waiting while it's just waiting for the result. While if we use CUB instead, so if we use transform instead of tabulate here, it will achieve the exact same results. The only difference being that here, the CPU never waits. So no matter the size of the input, no matter the number of elements we need to process on the GPU, the CPU will always wait around the same amount of time, which is just the smaller amount of time it needs for CUB to tell the GPU to launch the computation. So the CPU tell the GPU launch, that takes a small amount of time, and then the CPU gains control again. So you don't need to wait for the GPU to be done. So no matter the size of the input, your CPU will always wait for a very small amount of time, no matter the size of the input. And if you wanted to have the exact same behavior between the CUB and thrust, you could just simply add a CUDA device synchronize, which tells the CPU to wait for the GPU to be done before continuing. And so this will make CUB and thrust behave in the exact same way. So now that we know that CUB can launch a synchronous operation and thus leave the CPU running, and thus it can do other operation, how can we take advantage of asynchrony in our code? So when we launch asynchronous work with CUB, the CPU, as we said, is freed immediately. So it can do any operation while the GPU is doing something else. So here in our case, we can start the writing data to disk while the GPU is computing. So while the GPU is doing the simulation computation, the CPU in parallel can do the write to disk. And so then we need to synchronize with the GPU only after it finishes the simulation step. So since we would have waited for the GPU anyway, we're not losing any time. Instead, the wait step becomes shorter, leading to more efficient use of the system. And so as a result, we can expect a significant performance boost from this approach, because before we were waiting, doing nothing on the CPU, and now we take advantage of this step to write to disk. So before we were doing copy from device to host, then write to disk, then call thrust tabulate, which calls CUB, which do the computation on the GPU and then waits before again doing copy, then write to disk. Now what we do is we copy from host to device, from device to host, then we call CUB, which will do the computation, and while the computation is taking place, we do the write to disk. This way, we have in parallel two things going on, the computation on the GPU and the CPU writing to disk. But then we don't need to forget to wait, because before the next step, we will copy again, so we need to make sure the next computational step is done before doing the copy. So for this exercise, you will need to replace thrust tabulate to instead use CUB device transform in order to go from a synchronous code that needs to wait for the data into an asynchronous code where the CPU can write to disk while the GPU is doing some work. So you will also need to not forget to call CUDA device synchronize to make the CPU wait for the GPU to be done at the correct place to make sure when you're doing the copy that the data has indeed been processed. And so to do this exercise, you will have 10 minutes. And so you can find this exercise in the section 2, and it's exercise 2.2, exercise compute IO overlap. So time's up. Now let's see the solution. So all we had to do was to replace thrust tabulate with a CUB device transform in our simulation function. And so since tabulate is just, as we saw in the first section, a transform with a counting iterator, we can just do the same for CUB. We can use transform, and as an input, we take a counting operator. It does the same thing as what we did with thrust when we used thrust transform with a counting iterator. But now, because we're using CUB and not thrust, this is asynchronous. And so this allows the CPU to do some work, in our case, writing disk, while the GPU is busy doing this transform operation. And so after doing the simulation and the store to disk, we must add this CUDA device synchronize explicitly, because again, all the simulate steps will happen asynchronously. And so then when we reach this line, we might go here and start a copy. But so before, we want to make sure that the write to disk did happen before we override this hprev vector, because here we need to write it to disk. So we need to make sure that the CPU and GPU are both on sync after the simulation and the store before continuing on to the next step. Now we'll introduce something called Nsight System, because as we dive deeper into asynchrony, it might become tricky to understand what's going on and to debug and to track down performance. And so it's not easy to understand what is going on the CPU and on the GPU because it's happening at the same time. That's why at NVIDIA, we use Nsight Systems. And Nsight Systems is a software that allows you to visualize your program both on the CPU side and on the GPU side. And so you will be able to visually see when the CPU is doing some work, when the CPU is launching some asynchronous work, and when the GPU is doing some work. And you can all visualize that in a timeline where you will see, as time moves on, what is going on either on the CPU or on the GPU. So in this next exercise, you will learn how to profile your code with Nsight Systems. And so to do that, you will use the command line to call Nsight Systems that will collect some performance data. So first, open this exercise 2.2.3, and then execute this to generate the Nsight Systems report. And then once you have created this Nsight System report, you will be able to open it in Nsight Systems. And so to do that, you can click on Connect to Nsight Tools UI, which you will find here in the Nsight System drop-down menu. And this will open the Nsight System UI. And there you will be able to visualize your Nsight System reports. And so it will look like this. So here you have a tab with Nsight Systems. And you will be able to open reports. So you just have to click on File, Open, and then here select the Nsight System report that you just created by executing the cell. And then you can visualize what happened between the host and the device. You can even select a time region to visualize exactly what happened on a specific time region. So for example, if you want to see exactly what happened between 0.5 seconds and 0.7 seconds, so in this 0.2 second time frame, you can hold click, select this region, and then this menu will happen, and you can click on filter and zoom in. And so that will zoom on this 0.2 second slide of your whole execution time and filter only the things that are happening in this 0.2 section portion. And once you're zooming on it, you will find the hardware section, where this is where the GPU is doing some work. So you can see details on what the GPU is doing. And you can also see at the bottom what's here going on the CPU. And so you can, if you want to see what's going on the GPU, you can click on this arrow to unfold it and see all the details. So you exercise here is to generate the Nsight System report, open it using Nsight System, and try and understand when GPU's computations are being done, when is the CPU launching computation asynchronously on the GPU, when is the CPU writing on disk, when is the CPU waiting, when are the data transfer happening, all of that. So take your time, you have 10 minutes to open the reports and really get familiar yourself with the tool and probably get where is everything going on. Okay, so if we take a look at one portion of time where we're doing computation and writing to disk, this is what we're seeing. So we start with the write step when we're doing a copy from the GPU to the CPU. So this is what's going on here.
Then you can see how the computation is initiated by the CPU, but actually run on the GPU. So that's what's happening when you're calling thirst for a cow. We're calling it from the host or from the CPU. So there is sometimes to launch the computation. That's the small amount of time we need to wait. Then the GPU will actually run the computation. And so what we're seeing here, the CUDA device synchronize, is the CPU waiting for the GPU to be done. So here the CPU is launching the work. A lot of work here is being launched. And this is the actual result of those launches being ran on the GPU. That's why here, this CUDA device synchronize is taking a lot of time on the CPU because it's waiting, all this time is waiting for the GPU to be done with all this computation that was launched from the CPU. And the cool thing with all this time that is taking by the GPU to do the computation is this allowed us, because now it's asynchronous, to do the input-output writing in the meantime. So this is the CPU timeline, and we can see here that the write to disk is happening. So we're doing an fopen to open the file, a write to write to the file. So this is disk input-output, and finally closing the file. And we don't really mind this taking a lot of time because in any case, the GPU is doing some work in the background. So in the end, we'll have to wait for it anyways, because it's doing the simulation takes some time. So it's okay that this write to disk is taking a long time because the GPU needs a longer time anyways. So because we are able to overlap those two, the CPU taking time here is not an issue for us. And what's better is at any point here in this time slice, both resources are being utilized, both the CPU and the GPU. And again, this is thanks to Nsight Systems that we were able to visualize properly what's going on between the two. So if you profile the earlier version of our simulation, you'll see a clear performance difference between the synchronous and the asynchronous version. So here you can see that each time we do a CPU call, it gets mapped to a GPU call right away, and each time we need to wait. That's why here every single CPU call to the function thrust tabulate is mapped exactly one-to-one to one GPU call function thrust tabulate, because we wait between each of those. And finally, once all of those are done in a synchronous manner, only then we have the write step, which takes quite some time. While here on the synchronous version, we launch very rapidly on the CPU all those calls to the GPU, again, because we use thrust and it's asynchronous. Launching those is very fast because we don't actually wait for the GPU to be done. And then while the GPU is computing asynchronously, we're doing the write to the disk. And then before doing the next step, we need to synchronize. But so between the two, we are about 2x faster because we didn't have to wait. So analyzing these those differences between the two files still involve matching what you see in the timeline with your code, which can be a bit cumbersome. So fortunately, we have a tool which allows us to visualize easier what you see in Nsight Systems with your code, because right now we need to manually look and try and see and understand what's going on everywhere. And that's what we call NVTX. So when you are working with a complex application with many functions and GPU things and CPU things going on everywhere, what we'll usually use is NVTX. So NVTX is NVIDIA Tools Extensions API, and it allows you to insert custom markers and ranges directly into your code, so that when you view your Nsight System report, you will see labels. For example, here you can see in my for loop, I'm adding a range with a specific name. I'm calling it write step, and I can add the write ID. And this way, when in Nsight System, I will try to visualize what's going on, I will see that the write steps that is here is actually composed of this fopen, this write, and this fclose. And that is because I use a scope range, which means that this range will remain active for the whole scope of this for loop. And inside this for loop, I'm doing the write to disk, which is again composed of this fopen, write, and close. But now I don't need to even know that the write is actually doing an fopen and a write and a close. All I need to do is that at this stage, I'm doing a write to disk, and that write to disk, I will see because I added an NVTX range. And whenever I go out of the scope, this NVTX will be stopped. So here, your exercise will be to annotate
all the different steps. So we have the copy steps, we have the compute step, and we have the write step, and we also have the waiting steps. So we will have to add NVTX ranges everywhere to be able to better visualize in systems everything that's going on. So first the copy, then the compute, then the write, then the wait. And this way you can see everything properly. So for this, we will have 8 minutes. So if you have annotated things properly, this is how your Nsight system view will look like. And you can see here, it's way easier to see and understand what's going on. Here on the CPU, we first do the copy. Then on the CPU, we launch the computation. That doesn't mean we do the computation. We just ask the GPU to start the computation, but the CPU to launch many computation. Again, it needs not a lot of time because it's not actually doing the computation. It's just telling the GPU to do so. Then we have the very lengthy write to disk, which is here. And finally, we have the wait, which just waits for the GPU to be done. On the opposite side, if we look at the GPU section, we can see here that we first have the copy step, and then we have the compute step that takes most of the time. It makes sense because we're doing a lot of computation on the GPU. But here we can now clearly see what's going on between the CPU and the GPU. So at this point, we have learned how to use Asynchrony to overlap CPU and GPU tasks, leading to a big performance speedup because we were able to overlap the write to disk from the CPU with the GPU computation. So our code now copy data from the GPU to the CPU, launches an asynchronous computation with CUDA, and then write the result to disk. However, we still have room for improvement. The GPU compute doesn't actually have to wait for the copy to finish. We can apply the same overlapping strategy to the copy and compute step. But this will require the copy to be asynchronous, which currently it is not. Thrust copy is implemented with a lower level API called CUDA memcopy async. And this function can copy data between the host and device memory without blocking, so without being synchronous, so while being asynchronous. So let's take a closer look how we can use it to overlap our copy and compute step. So let's first try and understand how CUDA memcopy async is being called by thrust copy. So just know that memcopy async is not there is not tape size, operating byte, not element. You need to explicitly specify the copy direction, and the async errors can be easy to miss. That's why usually we call it thrust copy. But so CUDA memcopy async takes as input 4 parameters. First, the pointer to the destination memory address when we want to copy, then the source memory address from which we want to copy, then the number of size in bytes to copy. So it's not the amount of elements, it's decided in bytes. So if you are using integer, for example, you need to multiply the amount of elements by the size of 1 byte. And finally, what kind of copy you want to do. So is it host to host? So CPU to CPU, is it host to device, device to host, or device to device? So one subtlety of asynchronous operation is that errors don't always surface when the error occurs because it's asynchronous. So maybe you have launched something, the GPU is doing something, and then you get the error later because it's asynchronous. So the error on the GPU may arrive later than from the CPU standpoint. So for example, you could launch a kernel that goes out of bound, but the GPU doesn't actually start executing it right away. So you can only see the error right after. So meanwhile, you might launch another kernel, which also doesn't observe the error from the prior kernel, this one. And since it hadn't already just begun to run, right, you launch another kernel, but the first one isn't even running yet on the GPU. But then the board kernel here starts running, and after that, you launch a CUDA memcopy async here. This launch will discover the error, but coming from this first earlier kernel. In other words, an error triggered by any prior asynchronous operation might end up being reported by a completely different call. This is why it's crucial to check error codes after every CUDA call and be aware that an error can pop up much later than you might expect. So, while simply swapping here in our example thus copy for CUDA copy async be enough to overlap compute with copy? Not really, because by default, all GPU operations are ordered on the GPU end. So even though you're calling CUDA memcopy async and it's non-blocking on the CPU side, so the CPU will launch the memcopy and then come back, the GPU still executes it in order with everything else, just like any other earlier asynchronous computation step. This means that the GPU will wait for the copy to finish before proceeding to the next computation step. So it will first hear the CPU is asking for an async copy. So this work will be forwarded to the GPU. So the copy device to host will happen. And only once it's done, that then the compute will start. Those two by default will not overlap. They will go one after another because you ask for the GPU first to do one thing and then to do another thing. So by default, it will do them in order. So first do the copy device to host, which happens on the GPU, and then the compute. So right now we don't have any overlap between copy and computation. So the controlling the ordering of operation is what we call a CUDA stream. So by default, if you don't specify a stream, the default stream will be used, which means everything will happen in order on the GPU. So from the CPU, you're launching an asynchronous copy and an asynchronous computation using CUDA. But from the GPU perspective, all you're doing is stacking operation, which is here a copy device to host and a computation on the same CUDA stream. So on the same stream of operation, everything will just add one after another, and everything will be computed one after another. So we don't have to use the default CUDA stream. We can create our own CUDA stream, actually as many as we need. So when operations run in different streams, they are no longer ordered with respect to each other, and they can be executed completely concurrently. And that's exactly what we want, right? If we send the asynchronous copy in one stream and the compute in another stream, then those two operations can overlap. So here you can see we're launching an asynchronous copy from the CPU to the GPU in a copy stream, which is the first stream. And so then on the CPU, when we launch the computation, because we launch in another stream, when the operation finally arrived on the GPU, both the copy from device to host and the computation can overlap and work together because both of the operations are launched in different streams. So let's see how this works in practice. So that's what kind of operation we can use on streams. So we first declare a stream object. So here in our example, a copy stream and a compute stream. Then we have the construction step, which is just to construct a valid stream out of just a plain stream object. So to do that, we call CUDA stream create, which will actually allocate the stream. So now our copy and compute stream are ready to be used. Once we're done using them, we need to call the destructor. So we need to call CUDA stream destroy to destroy the streams once they're done being used because they have been allocated first. And whenever we need to synchronize, we can use CUDA stream synchronize, which will wait on the CPU side for all operations that were added to the stream to be done. So if on one stream you added 100 computation, calling CUDA stream synchronize will make the CPU wait for all those hundreds computation to be done on this stream before doing anything else. This will not wait for anything being launched on any other streams. This only blocks the CPU to wait for all operation to be done on this specific stream. That's why in general, we advise to explicitly use streams and not use the default stream and use CUDA device synchronize, because CUDA device synchronize will cause the CPU to wait for all GPU operations on any single stream to be completed. So maybe you are doing 100 different things on 100 different streams, and just by calling CUDA device synchronize, maybe you just need to wait for one of those, but you're actually waiting for the things to be done on all 100 streams. That's why in general, you don't use CUDA device synchronize, but instead you use CUDA stream synchronize to wait for things to be done just on the specific stream you care about. So you will find streams in most of obviously of the CUDA libraries we are developing at NVIDIA, because we want to make everything asynchronous and be able to overlap. So in CUDA memcopy async, obviously you can pass a stream to make the call not only asynchronous, but also be able to overlap with something else. When you're using cub, you can also pass a stream if you want your operation like a transform to be not only asynchronous because we're using cub, but also be able to overlap. And same goes with most of the libraries we have, like QFFT, QBLAS. Here, same goes for QBLAS. We have a stream parameter, which again would allow us to do some overlap. So let's start by creating a CUDA stream for compute and copy. So here we declare two streams, one for compute, one for copy. And we allocate the data by calling CUDA stream create on both streams. Then we call CUDA memcopy async, passing the copy stream to launch an asynchronous copy. So the CPU will ask the GPU to asynchronously launch a copy on the GPU, while the CPU can continue on with the rest of the code. Not only that, but on top of that, this copy will take place on the copy stream, which means that next, when we launch the compute by using cub, because to cub device transform, we are passing these compute streams, both this copy here and this compute here, both things will happen in parallel concurrently on the GPU, because both of them are launched on the different streams. And then, because the copy here happens asynchronously, we have to make sure that it actually finishes before reading the host data. That's what we need to call CUDA Streams synchronize on the copy stream before launching the store to disk, because here we're copying in hprev, and here we're writing to hprev, because this is asynchronous. This is asynchronously going on the GPU. We don't want to start doing the store while the GPU is still doing some computation, right? We need to make sure that this copy device to host, which copy hprev, is done before doing the write on the disk. So to do so, we just need to synchronize just the copy stream. We don't care about the compute stream here. We just want the copy stream to be done. That's why we use CUDA stream synchronize on the copy stream. Then we can launch the store that writes to disk. And only then we also synchronize the compute streams before going on to the next step. And congratulations, we've just introduced our first data race. So let's walk through the first few iterations to see why. So we use a copy from dprev to the host. That's what we're doing here. The first compute iteration reads from dprev and writes into dnext, which is fine. That's what we're doing here. But the next iteration reads from dnext and writes back into dprev here. Because this operation runs in different streams, the GPU can interleave them in an unexpected way. This means that while data is still being copied from dprev to the host, it might get override by the next compute iteration in another stream. So again, here we're asynchronously copying the dprev pointer into hprev, and in parallel, we're computing dprev into dnext. For the very first iteration, that's okay. We're computing here into this. But at the next iteration, we swap pointer. So now we're computing dnext and writing into dprev. But maybe the GPU here is still doing this device to host copy. So we just created a data race, which means that based on luck and how the program will run, sometimes we might find different results in this dprev pointer, because sometimes the computation will be done, sometimes not. And so we should find a way to solve this issue. So like many computer science problems, we can solve this by adding another layer of indirection. So we can allocate an extra device buffer to copy data into it synchronously, and then copy from that staging buffer back to the CPU. So since no one else is writing to the staging buffer, because it's just there for the reading, there's no risk of data race. But doesn't that defeat the purpose of overlapping compute with transfer? At a first glance, it may seem like so, but we've introduced additional work, which is another copy and an additional buffer. So surely this would make things slower, not faster, right? Well, if you take again a closer look at the bandwidth across your entire system, this approach makes a lot more sense. Copying data within the GPU can hit speeds of around thousands of gigabytes per second, while moving data in the CPU memory is slower. Moving data between the CPU and the GPU often go to what we call the PCIe bus, which is going even slower than what the CPU memory bandwidth can achieve. So memory copy from device to device is much faster than memory copies from host to host, which is also faster than memory copies from CPU to GPU and from GPU to CPU. So the device-to-device copy is going to be so fast that it's practically free compared to doing the host-to-device copy. That's why here, adding an additional device-to-device copy is not going to be an issue. So that brings us to our next exercise. So in this task, you'll replace thrust copy with CUDA copy async to make your device-to-host transfer asynchronous, and you'll also place your computed copy operation on separate streams and synchronize them exactly as shown on the diagram on the slides, as you can see here, as we have discussed. And finally, once you're comfortable with that, with the changes, you'll profile the code in Nsight Systems to see if it behaves as expected. And so for this, you will get 15 minutes starting now. Okay, so now let's walk through the solution. So first step, as we already have seen, is to create two streams, one for copy, one to compute, and allocate both streams. Then we want to synchronously launch the copy from device to device to copy our previous temperature into a staging buffer. And so this buffer will just be used for staging. So then we can at this point we can still use thrust copy here because device to device is generally very fast, and so we don't need to block. We don't need a synchronous launch here because it's very fast anyways because it's already on the device. And so this step ensures that the device data we copy to the host remains untouched by any subsequential computation, and thus preventing any data race. So this staging buffer is safe. And so after that, we invoked the asynchronous copy on the copy stream again by calling CUDA copy async. And since CUDA copy async operates on row pointer, we use thrust row pointer cast to retrieve the underlying pointer from the thrust vector. Finally, we update the curve transform call to run on the compute stream we created above. And by specifying the stream at the last parameter, we're telling cub to execute not only obviously asynchronously, but running asynchronously on this compute stream. And so this transformation that cub is doing is being run independently from any operation on any other stream. So in our case, the copies. After that point, we can proceed to writing the updated host data to disk. But before doing so, because the operations are asynchronous, we shouldn't forget to call CUDA Streams synchronize on the copy stream to make sure that the data has finally been copied from host to device before doing the store. And then we can finally synchronize the computer. So if we look at the Nsight system profile of such changes, we have both good and bad news. So the good news is that our intuition about the cost of data transfer was correct. The device-to-device copy on the left that we see here is significantly faster than the device-to-host copy, which is here on the host. So this, we were correct on this side. So it confirmed that the PCIe transfer is the real bottleneck here, and adding a device-to-device is not a real issue. So we don't have a race condition anymore. But the bad news is, even though we're using separate streams, we will use one stream for the copy and one stream for the compute. Here, there is no overlap, right? The compute is waiting for the copy to be done before launching. That doesn't make any sense. We have just learned about streams and that if we use separate streams, things should be run concurrently. And here we use stream for this very reason. And yet it's running just like we weren't using any streams. That's very weird. So we're missing something here, but that's great. That's
a new thing what we will learn about, which is pin memory. So to understand why our copy and compute operation that didn't overlap, we need to take a look at how memory actually works. So when your program uses virtual memory, which is divided into memory, what we call memory pages. So most of the time, those memory pages, they're backed by physical RAM. But if the RAM is short on space, the operating system can swap pages out of the RAM memory into the disk, so on your actual hard drive. So this means that at any given moment, you can't be entirely sure that some memory pages might be on RAM, it might be on disk, you never know. So to make sure that a specific page of memory is on the RAM and that it will not be put on the disk, we need what we call page-locked memory or pin memory. And so by pinning those memory pages, like you can see here in the RAM, you're sure that the operating system is not allowed to move those memory pages from the RAM back onto the disk. And so those memory pages, they are locked, they're pinned, that's why we call them pin memory, they're locked onto the RAM. And so how does this has anything to do with the GPU? Well, as it turned out, the GPU can only read memory from the pin memory. So when it's in RAM. So that raises the question. We haven't done anything special for now to transfer data between CPU and the GPU. So how do things work in this case where data could be on the RAM or on the disk? So behind the scene, the CUDA runtimes uses a small pin buffer at the staging area for transfer. So when you copy the data from regular, what we call pageable memory, the driver moves the chunk of data into the staging buffer, which is pin, and so send that chunks to the GPU, waits for it to finish, and then repeat the process again and again. So this process effectively makes the copy synchronous, even if we used CUDA memcopy async, because it blocks everything else from happening because it needs to do this process over and over. So the good news is we can avoid this allocating of pin memory here of the staging buffer by allocating it ourselves. So in Thrust, we have a simple interface, what we call the universal host pin vector, that allow us, instead of using a regular host vector, this memory is guaranteed to be pinned. And so this way we can bypass this hidden stage where the copy is happening synchronously to make sure that the data is in a pin buffer. So this brings us to the final exercise of this section. So this time, instead of allocating a regular host vector, we want to allocate a vector that we're sure the data will be backed by pin memory, not by memory that might be on the disk. So instead of using a host vector, we want to use a universal host pin vector. And so after making that change to the container, then you will launch Nsight Systems to see the difference and visualize it. So for this exercise, we'll have 5 minutes. So here's the solution. So the change is pretty easy, right? Just instead of using a Thrust host vector, you instead use a universal host pin vector. And with that done, the device to host transfer now overlap with compute. So as we can see on the timeline, the GPU here can launch many compute operations one after another, while this device to host a memory copy can occur. This is because now it knows that the data is in the pin area, so it doesn't need this initial step of copying the vector chunk by chunk in the stage pin area before doing the rest. It can directly do both of those in parallel. So that's how we were able, using streams and pin memory, to overlap device to host transfer and the computation. And so this, again, has improved the efficiency of our program. So the key takeaway of this session is, first, prefer asynchrony when you can overlap host and device. So when you have some time to spend on the CPU, so when you open Nsight System and you see you have some times where the CPU is doing nothing while there is actually something it could do, like in our example, write to disk, you should swap Thrust to CUB to instead use our asynchronous programming model, and this way be able to overlap
CPU task with GPU tasks. So as a reminder, when we call CUD, it's the host is launching computation on the device in an asynchronous manner, which means it doesn't wait for the GPU to be done. So no matter the size of the problem you're trying to solve on the GPU, the host will go back almost in an instance, and then the CPU can continue on by doing anything it wants, while the GPU is doing some computation, maybe very lengthy, in the background. Then we saw how using Nsight Systems, we were able to profile our code by generating a report and opening it and being able to see what's going on both on the CPU, on the GPU, and see when we are wasting time or when the GPU is not busy enough. And it also allowed us to visualize our asynchronous operation. We also talked about how NVTX allowed us to make this visualization way easier by seeing exactly what things happen where in the code by manually adding ranges where it makes sense, so that we can directly map the code to the Nsight system report. Finally, we said that, okay, Asynchrony through CUDA allows us to parallelize work between the CPU and the GPU, but we have seen how using CUDA Streams also allowed us to make work in parallel on the GPU. So for example, when we had one step which was a compute step and another step which was a copy step, and the two could be done in parallel, well, instead of running both sequentially, we could overlap them by using different streams, because if not, by default, everything will be launched on the default stream on the GPU, and so all the work will be run one after another. And because here the copy and the compute could be run in parallel, we should use different streams. We also talked about how CUDA copy async would allow us to launch not only async memory copies from host to device, but also allowed us to add this stream parameter. And this way, we were able to launch copies not only in asynchronous manner, the CPU was free to do something else, but also it would allow us to launch things on one stream while we were doing computation on another stream. Finally, we have seen that doing copies from host to device can be costly because data by default is pageable, so it may be on the disk. And so to make sure that copying is fast and non-blocking, we should use the right thrust host container to make sure that the memory is pinned, and thus that the copy is non-blocking and fast. So that concludes our section on Asynchrony and CUDA Streams. Again, if you have any feedback, please put them on the TLI website.